An important thing to develop in somewhere in your brain is that when you see something that looks like this, where your initial, like your surface reaction is probably, for the love of God, what the heck am I supposed to do with this? You know the answer, okay? And this is where you're catching up with yourself on the 2-1 and how you disciplined your brain to think about all those properties, because this is a property problem, right? So first of all, in a big picture way, this is the limit of a product we're being asked to find, isn't it? Because when I'm asked for the limit as x approaches infinity of y, and I can call it y until I start breaking it apart, what is the limit of a product? The product of the limits, okay? So this is equal to the limit as x approaches infinity of 2 minus x over x plus 1 times the limit as x approaches infinity of x squared over 5 plus x squared. Now, I'm going to do this in great detail because that's the way you're supposed to approach these problems. And the way you know that you're supposed to do it this way is that all you can do is apply the properties if these are gray bubble problems, which means do not touch your calculator, right? Okay? So far, so good? Now, when we finish this, we're going to come back and look at sort of a cheat, that's C-H-E-A-T, cheat way to do it. And then you're going to be like, oh, but that's not an okay way to do this problem. This is what I should see on your paper. Follow me? Okay. And the cheat way will help you when you start doing multiple choice questions on the AP exam. And as you might recall, when I give you a multiple choice question, whether it's on homework or on a test, I expect you to defend your answer, not just write the answer, okay? So let's get back in the habit of doing that. All right, so let's see what happens when I go to take that first limit. Well, now that I've separated it out as the product of limits, what is my first limit? It's the limit of a difference. So then this is the limit as x approaches infinity. Now, as you're writing this, you're like, dear God, how many times do we have to write this? Well, this is to force you to reckon with the fact that you know how to do this if you just take the limits individually. You got me? All right. So then I have a constant, right? And we need parentheses around this, right? Minus the limit of, as x approaches infinity, of what? X over x plus 1, right? And then we're going to need our other parentheses because now the other thing in the product is a limit of a what? Quotient. So then that means this is what? Quotient of the limits. So this is the limit as x approaches infinity of x squared over, about to go skip the limit notation, the limit as x approaches infinity of, in parentheses, 5 plus x squared. Now the good news, if there is any for you at this point, is that we're not going to write the next step we could write because once you've written this step, you should have your brain heading in the right direction. You with me? Okay? So now we'll go back and think about these as we go. Well, in my first factor, I have the limit as x approaches infinity of 2, which is what? 2. Why? Because the limit of a constant is that constant, right? Always, because it's a horizontal line. Okay? Minus, and then I have the limit as x approaches infinity of x over x plus 1. All right? Well, what did I tell you yesterday for the very first part of our notes? And I said this is kind of a thing that you really want to lock in about what is the limit as x approaches infinity talking about that we learned in pre-cal? Horizontal asymptote, right? Do you remember Twitty's quick test I taught you last year? What was the rule about rational expressions? Top heavy, bottom heavy matching? Which one are we in here? Matching. So what is my limit? 1. Because that's just a horizontal asymptote, right? Now, as I said, we could go one more step of this zoomed in approach that your brain should be taking, and we could rewrite the limit as x approaches infinity of x over the limit as x approaches infinity of x plus 1, but we'd wind up in the same place, wouldn't we? Okay? So then now we're going to do the quotient that we actually wrote out that way. So the top is the limit of a what? A power, right? And what is that?
The power limit raised to that power.
Right, it's the limit raised to that power, right? Okay, well what would that be? And we don't want to write it, but what would that be? Infinity squared, right? It's going to blow up, right? Is there a limit for x squared? No. All right, so we'll just put an infinity on top and come back to that, all right? And then on the bottom, how about that one? Infinity again. Well, that also is going to blow up. And technically, that is indeterminate form. So because of that, let's come over here and put implies. And then we're going to come back down to the bottom and put equals. What's 2 minus 1?
1.
Glad you still know that. All right, now let's talk about that infinity over infinity, which is technically not legal notation. But if you put implies, any mathematician who knows calculus would understand where you were going. All right, but let's go back to x squared over 5 plus x squared. If I'm treating that the same way I treated x over x plus 1, what am I thinking? 1. Why? Matching degree. Matching degree, it's the ratio of leading coefficients. So that's just 1. So this is 1 times 1, which is 1, not 2. And I say that because every year somebody on a calculus test somewhere does something like 1 times 1 is 2. Now, was that not more doable than you thought? Okay. So you will understand if you turn your 2-2 homework in with no work and I give you little or no credit. I don't really care whether you understand. It's just the way it's going to be. So make peace with that. All right, now let's talk about 23. And I normally wouldn't do back-to-back problems. And I also, while you were in your brain grumbling about the fact that you had to write all that out, I would point out to you that there are 3 of these on your assignment. So to be crude, suck it up. All right, so we have y equals cosine of 1 over x over 1 plus 1 over x. All right, well, if you were like having that little aha moment in your heads while we were doing 21, you should be able to tell me where we're going with this one. Oh, we didn't do the negative. Let me back up to 21. I just realized that we're supposed to do positive and negative. Now, I'm not going to make you write it all out, but once you've done the positive limit on one like this, you should think about whether it's still going to apply. Okay? You know what I mean? Like everything you just did. And one way to do that on your homework, for my benefit, instead of having to rewrite all this with all the negative infinities, is to come back and put a little plus or minus in front and see if that works. Okay? Now, I wouldn't write it till you had confirmed it works. All right, but clearly, if I put a plus or minus all the way across on that step, it's the same, right? Because all I had done is broken it apart with properties. All right, then, so what I really need to look at is the very last step where I transition from limit notation to constants, okay? Is the limit as x approaches negative infinity of 2 still 2? Yes, I put a little check for myself. Yep, that one is the same with a negative, right? So then how about the limit as x approaches negative infinity of x over x plus 1? Why is that the same? Right, it's still at 1 because even if my x's are negative, the negatives technically would cancel. Does that make sense? All right. How about the other factor where we did it as the limit of a quotient? That's why is that like emphatically the same? Because if you're going to square the x coordinate, the negative is not even relevant. Okay. So what we should write as a final answer, and I was negligent in not writing that, is that the limit, and I'll come back to my blue color I was using to write the final answer, the limit as x approaches plus or minus infinity, which I can write because we just confirmed that it's the same, of y equals 1. And the nice thing about this notation, as ugly as y was in its definition, you're allowed to do what I just did. Call it y, don't call it the right side when you're putting your final answer down. Does that make sense? Another little tip for you that will save some of your sanity between now and the time you finish the AP exam. So back to number 23. What are we taking the limit of here? What is this when they ask me to do a limit? Limit of a quotient, right? Okay. So that means that this is what? The limit as x approaches infinity. And after you've just done 21 and thought, well, wait, I could have just been doing plus or minus. I don't recommend that you think plus or minus the whole way through Because what really stinks is if you've been writing plus or minus on like the first 3 or 4 limits you write, and then you get down to the middle and realize it's actually going to make a difference. So I would do the positive version and then go back and think it through the way we just did that one. Does that make sense? So don't let me forget to come back to the.
Wait, I have a question on that.
Okay.
So, like, whenever you go through, you do the positive, you go back and check and say the negative works and stuff, like, do you have to go through and put plus or minus?
Technically, you should go back and put plus or minus on everything.
Okay.
Because otherwise, it's not that little equal sign that we've written so much that we don't really realize the significance of. We're saying two things are equal, but may or may not be equal. You see what I mean? But once I've confirmed it, I can go back and stick it
So
on
you
there.
do that and
Yeah.
then you also do level sentence.
Yeah, yeah. Well, the final answer should be stated anyway, right?
Okay.
All right. Okay. So now, what does that mean? Since we are taking the limit of a quotient, what is that? Quotient of limits. So I write the limit as x approaches infinity of the cosine of 1 over x over the limit as x approaches infinity of 1 plus 1 over x. Yes? When in doubt, use them. All right, but let's think about that. All right? If I'm taking the limit of one expression, like cosine 1 over x, or 3x squared, then there's only one thing, so I don't need parentheses, because I'm taking the limit of that term. But if I left the parentheses off the bottom, what the notation would mean is the limit as x approaches infinity of 1 plus 1 over x not having the limit taken of it. You see what I'm saying? Yeah. So that's something we'll work on, because that's a weak spot for Camden High students. I can vouch for that. Probably all students, but I only know Camden High students because that's where I've been for over 2 decades. Okay, so let's look at the top. Can we take that limit? Well, what happens when the denominator of a thing gets huge and the top is constant? Gets super tiny, and since we're looking at limits, what would eventually happen? It would be so tiny that whatever technology you're using would say, dude, this is 0, right? It would stop writing, 1.1 times 10 to the negative 27. You see what I'm saying? It would reach its capacity of digits or whatever and say 0, right? So we're going to write 0 on the top. Oh, I'm sorry, not 0. What is actually 0? The inside, right? So it's the cosine of 0. My bad. There we go. Cosine of 0. Yes? Because what I actually took the limit of was the x expression. Does that make sense?
Just to show that step.
How would you show that step? Right? I mean, does that make sense? X is gone now. I know that that's going to be the cosine of 0, which I already know what it is, but I'm going to write it so that the world will know where my answer came from. Okay? And especially for guys, that is a really hard thing to do. They're like, but I don't need that step. Like, I did it in my head, like at some point of pride that the fewer steps I write and still get the right answer, that makes me better somehow. Bad news, no. Because on the AP exam, that makes the difference between maybe a 3 and a 5 even, if you do it across the board. All right, so let's look at the denominator. This is actually a limit of a what? Of a sum. So let's go ahead and write that one out, again, to reinforce what your approach actually is here. So this is the limit as x approaches infinity of 1. Talk to me. Plus the limit as x approaches infinity of 1 over x. Yes? Okay. Is that a wait? Oh, you said right. Okay. All right, what is the cosine of 0? Did you say undefined? Whew, maybe I should go down the hall and come back and try that again. Sine cos. Where is 0 on the unit circle?
0.
And what are the coordinates of that point on there? 1, 0. Sine cos. What is the cosine of 0? Y'all need to work on your unit circle. You're going to be in a world of hurt. The longer you wait, the worse it's going to be. I'm just going to tell you. All the way down to, God forbid you make a 1 or a 2 on the AP exam. I think 2 is worse than a 1. I just do. Because for all you know, you were 1 point away from a 3, right? You'll discover that with the practice exams. Trust me. All right, so now let's look at the denominator. What is the limit as x approaches infinity of 1? 1. Love your enthusiasm. Okay. 1. Okay. What is the limit as x approaches infinity of 1 over x? 0. So we're left with 1 over 1, which is 1.
Answer is always 1.
That is such a 7th grade response. You remember when you did this problems, right? You do like, the teacher would do an example, the answer was 5, you do your first two and the answer's 5, you're like, well, I'm just putting 5 for everything, right? No.
Hundreds.
Okay, so now what else do we need to do? Check it for the negative possibility, right? Because our job was to find both in both directions. So I'm going to come back, and I'm going to be thinking plus or minus, but I'll actually put them on there this time, Madison. So I want to know if all this still works for negatives, right? So that would be the first time we wrote it with it broken out as the limit over the limit. So the limit as x approaches negative infinity. If I put a negative infinity there, what is still the value of 1 over x? When the bottom gets huge negative?
0.
It's still 0, right? So that's still cosine 0, so the top works. And then on the bottom, when I split it up and I've got the limit as x approaches infinity of 1, it's irrelevant, right? Because there's no x there. And then how about the next one? Same thing, so I can come back and sneak a little plus or minus in front of every infinity I wrote. And when you're doing a set of problems like this, you can do better than I did as far as leaving yourself room to squeeze those in. Does that make sense?
Yeah.
And if you don't really leave yourself room and you make it really tiny, I'll be able to tell you were attempting to squeeze that back in there. All right, so then our final answer is the limit as x approaches plus or minus infinity of y is 1.
Slam.
Is that better? And I'll tell you on 25 the answer is not 1. So if you try to make it 1, you're going to be struggling. You won't be struggling as hard as I have in the last couple of days trying to shake whatever virus I have. 33. Okay, the directions here say A, find the vertical asymptotes of the graph. If you picked up your calculator to do this, you should smack yourself. Okay? Then on the bottom, describe the, or not on the bottom, part B says describe the behavior of f of x to the left and right of each vertical asymptote. All right? Well, when I look at number 33, the fact that you are asking me for number 33 says, Dear Miss Twitty, I forgot any trig I might have known. And I missed the point of that day we worked on identities. Because if I have f of x, and just making sure I called it whatever they called it, equals the tangent of x over the sine of x, and I might be interested in seeing what happens when I simplify this. Why could you think of this almost as an unreduced fraction?
Because tangent is
That's right, because tangent is, and we're going to write it in like exaggerated vertical form and then we'll clean it up, is what? What is tangent? That is pertinent to this. It is sine over cosine, right? So this is sine x over cosine x over sine x. Dividing by a number is the same thing as multiplying by its reciprocal. So we get sine x over cosine x times 1 over sine x. So what we're left with is 1 over cosine x. Now, we don't need to convert that because it's going to help us to leave it in that form. Right? And why you would leave it that way versus not leaving it that way has to do with what it is you're trying to do. What is my job to do here? Figure out where there are vertical asymptotes. Okay? So now, with it written as 1 over cosine x, what do I know? What can the denominator not be? 0. So I know that I have for part A, and notice I kept writing equals, it's because I was just rewriting the original function. I have not done any calculus, right? Okay? If it's 0, I don't know what you No, yeah. The cosine of x, okay, I was like not processing what you're saying, but yes, that's correct. The cosine of x is 0, not the value is 0. Do you see what I'm saying? And we're not saying the cosine of 0, we're saying that when the denominator equals 0, right? Okay, so if I write this on my paper, and this doesn't look like really formal and analytic work, but it would communicate to anybody that knows what you're doing. If I'm looking for a vertical asymptote, it would only happen when the denominator, which is cosine x, is 0. Now do you see why I say we shouldn't rewrite it? Because I could write that as secant, but I'm not going to think better in secant, am I? Or am I?
No.
You should. And I'll catch you on that in just a second. All right? Because now I want to go back and I'm going to write it. It's like, dang it, just when I thought I knew all the right answers. All right? I'm going to come back up here and write this in a different color. Now I want to write secant x. Why? Because I should know what the graph of secant x looks like. And you're like, Wah, wah, wah. Okay. If you will recall, yes, it looks like a bunch of parabolas. Well, where do they sit? Well, since it is the reciprocal of cosine, if I can think, and I'm going to come over here to a clean screen and sketch this. I'm really glad I used the graph paper background. I think Jesus told me to do that because I wasn't really sure why I did it, but now I know. All right. Don't laugh at me. Okay. What does cosine do at the y-axis? It's at 1. So I could start it up here, right? And then I could kind of just sketch it out from there. Just because this is just a sketch for me to think on paper. And you should probably have this on your paper, given that I'm the one that's doing the problem and you won't remember where we got all this. Okay? And so the secant graph sits on the peaks thusly, so that at every top peak, I have a U-shaped looking thing, right? And on the dips, I have an upside down U-shaped thing, right? So my job here is to figure out where these vertical asymptotes are that happen in between. Well, that should be pretty easy if I remember where they happen. Where do they happen? Where cosine x is 0, okay? So where would the first one be? At pi over 2, right? Straight up. Where's the next one? 3 pi over 2. Yes?
Yeah.
Where would the next one be? 5 pi over 2. Well, if I went in the negative direction back over here, if I go to the left, where's the left one over there? Negative pi over 2, which is also 3 pi halves, right? You with me? So now I know where my vertical asymptotes are, right? So I'm going to come back and write that down. I have vertical asymptotes at, so I'm going to put it implies behind my cosine x equals 0. So we have vertical asymptotes at x equals, what did you notice about the coefficient? And this is one way to do it. You can write k pi halves and then put in parentheses k, an odd integer. Does it make sense? So all the odd multiples of pi halves. I don't want to count the even multiples of pi halves because it's okay if those happen, right? Because that's where we're going to get 1 or negative 1. So that's my vertical asymptote. Well, while I was thinking on paper to figure that out, I'm actually sort of answering the part B of this, which said describe the behavior to the left and the right. Because I drew a rough sketch, but it's accurate enough to answer this question, right? Well, look at the two that we included, or at least I included in my sketch. Is the behavior the same at both of them? What happens to the left of pi halves? What does the graph do? Shoots up to infinity. How about to the right? Shoots down. So let's jump over to 3 pi halves. What happens to the left? Shoots up. To the right? Shoots down, right? So we can trust that this is going to happen every time, right? So we're going to come back and say for B, in fact, I didn't really leave myself room, so I'm going to slide over here and write it. In fact, I'll write it down here underneath this. No, I'll put it on the screen. All right, so B, at each vertical asymptote,
I have a question.
yes,
On the graph, isn't there another vertical asymptote where it hits the graph in between those two?
yeah, you're right. Well, actually, I labeled the wrong one. That would be my 3 pi halves. I was not paying attention to where I was, but yeah. So technically, we should have 3 in there. Yes? So this is 3 pi halves. So that would be 5 pi halves. If you didn't know that, y'all need to study your must-know functions packet. Oh, by the way, I do have those copies for y'all that asked for them yesterday. So when you get ready to leave, if I don't happen to be standing up here to remind you where it is, if you look in this file box, you'll see colored paper. You can grab them. There's 3 different color choices, and there's one that's half green and half purple.
Oh, that's me.
You want that one?
I'm just joking. I don't care.
You are so special. All right, so, but nonetheless, we do know what happens at each of those vertical asymptotes. It's the moral of that story, right? Okay? And so since that graph wasn't part of my answer, even if I made the error that I made, like as a student, I wouldn't get docked because my answer would be graded. Because that was just me thinking on paper. That wasn't even showing evidence, right? Because ultimately, you don't want to have to draw that picture. Ultimately, you want that picture to pop in your head, so you shouldn't have to write that on paper. You got me? But if you need to, sketch it out because it'll help you. All right, so at each vertical asymptote, the limit as x approaches infinity, as x approaches k pi halves from the left, and what did they call this? F of x, right?
Well, wouldn't that be different because like the one we just drew on the left side it's going down and on the right side it's going up?
Yes.
Like in the back of the book it had like one, like let's just say like your first vertical asymptote is like A and like another one and then like B. So you could say like on the left of this one and on the right of this one and then on the left of this one and on the right of that one. So like because
There's other ways to do that. Okay, so we'll back up to our answer. At least we know somebody's paying attention and thinking. So it's not x equals k pi halves, is it? Or yeah, it is. Because that was just the asymptotes, wasn't it? Yeah. So we were okay with that. All right. So now our end behavior is going to be different, and we're gonna and there's ways you can do this, and I'm going to show you one of the ways to handle that. All right. So the limit as x approaches k pi halves, and what do we define k as in our first part of our answer? The odd multiples, right? So how can we define that differently? Well, we're going to say, in fact, let's use a different letter. That's probably the easiest way to do it. So let's call this, I don't know why my pen's not wanting to write, c pi halves. And then put c equals, and we'll put this as set notation, and you're going to put ellipses on the left, and skip a space and come over here to, what was our first one on the right, positive side? And that would be where c would equal 1, right? So we're going to put 1 here and negative 1. Yes or no? No.
I am so confused.
Yeah, so
It's because y'all don't know your trig like you're supposed to. Okay, let's go back to the picture. All right? Okay, let's go back to the picture. This picture should be on your paper, and it should have been corrected when Morgan pointed out that I skipped one of the vertical asymptotes. Which I wasn't drawing it for me. I was drawing it to try to get you thinking, and I was hoping I would hear this, oh yeah. I didn't hear that. Okay? So, does everybody get it now? All right? The behavior's not the same. It's the same at every other one. Right? Does that make sense? So now we're trying to put in variable notation what's actually happening instead of that the same thing is happening everywhere. Yes.
In the packet, I think you gave us, so you gave us in the packet.
But you know what? You're not going to have the packet. Y'all need to study the packet, but you're not going to, I'm not, and we already know what the asymptotes are. We've already described them, right? We're describing the behavior at each one, which it alternates. Does everybody see that? Because at the first one, it's to infinity and then to negative infinity, left and right, yes? Then the next one is what? Negative and positive. And then what? Positive, negative. So it alternates. So we're trying to summarize that in an answer, in a coherent answer. Okay? So now I've converted my C to a K, my K to a C. Why did I do that? Because I don't want all the K's included in this. I want just the ones that it's applied, that it holds for. You with me? Okay. So now go back to your picture if you need to. All right? Well, why, and I didn't continue my picture, and I'm not going to. Use yours and think it out. Is whatever happens at pi halves going to be the same thing as what happens at negative pi halves? No, it's not. Why not? Because those are one right behind the other, right? Those are adjacent, if you want to think about it that way. They are adjacent vertical asymptotes, aren't they? Where the function alternates its behavior. Yes? So it's not the same. You with me? So what do I need to do to list my set notation? And I'm using set notation because if you don't understand what's happening already, I clearly don't want to use some other more abstract way of doing this. And there are more abstract ways which we will get to over time. Okay? So we've confirmed that it's 1, yes? When C is 1, which would give me pi halves, right? Okay, now let's go in the positive direction. Would 3 work? Because I know it's odd, right? Not 3. So what would it be? 5. And then it would be? Why? Because it's every other odd number. So I put comma, ... Because the more abstract notation here that you will eventually learn to write will start if you write these numbers out and think about the pattern in them. Okay? So now we're going to back up and do the negatives. We said it's not negative 1, right? Because that would be the adjacent or adjoining vertical asymptote, if you want to think about it that way. So what's the first one? Negative 3, negative 5.
7, negative 7.
I'm sorry, you're right. Hey, you do get it. I'm just trying to move on.
Just had to get really slow and go retard for a second, and then I got it.
Well, but you know, that's the thing. And don't you feel like that was the same thing with 21 and 23? It wasn't that y'all didn't know everything. You weren't, it's not that you weren't equipped to do the problem. You didn't know which toolbox to pull from, right? But that's what takes practice, all right? So we have the limit as x approaches c pi halves of f of x. Yes, isn't that what we call it? Because I don't want to have to write that tan x over sin x again. I'm lazy. Okay, good mathematicians are lazy on paper. They only put what needs to be said to demonstrate that their answer is correct. So that's from the left, yes? For all of those from the left, what happens? It's infinity, right? Well, the great news is that if I go to write the other possibility, I've done all the thinking I need to do to be able to state this one directly, don't I? Haven't I? Okay. So now I'm going to say the limit as x approaches d pi halves. Oh, wait, we haven't done c yet. My bad. Because we got to do from the right now. C pi halves from the right. Okay? So we're still doing c. So now it's going to be of f of x equals negative infinity. All right? Now, let's let that kind of sit for a second. And over to the right, and I'm going to go to a new screen because I wrote too big to write it on here. But where we wrote our definition of c, now let's define d. Because then y'all should be able to go back and write those limit statements knowing what d is, right? Okay? So what will d be? It will be all the odd numbers that c is not, right? Okay? So if I come over here, sort of leave some space so I can put some negatives in, I recommend that you always do this. Just put a comma, and after that comma, we're going to write our first odd value that wasn't c. So that's going to be 3. And then we're not going to include 5, right? Because we are, what are we doing with these odd numbers? Every other. So if we start with 3, what's the next one? 7. Let's go one more. 11, comma, dot, dot, dot. So what that says at the end is this goes on forever. Now we're going to back up to our negatives, okay? What was the first negative value that c was not? Negative 1. And then I don't want negative 3. I want negative 5, dot, dot, dot. Got it? So then y'all should be able to go back and write those limit statements, because what's going to be true about these limit statements? They're going to be the opposite. So where one was positive, this one's going to be negative and vice versa, right? I love those problems because that's how you kind of find out where you are with your trig knowledge. You're like, thought I knew it. Pagans. $41. Oh, come on, pen. Don't do this to me now. Sometimes it just quits, right? Yeah, there was a circle there. 41. The directions here say, all right, where was the ones I was supposed to just read you the directions, Marquise?
49, 51.
Okay. Don't let it sneak up on me. All right, 41, the directions say, find a power function in behavior model for f. Really? Identifying horizontal asymptotes. Really? I'm really doing 41? I'm doing a pre-calc problem for you? F of x, that's so crushing since I was your pre-calc teacher. 41, we have x minus 2 on the top. Over 2x squared plus 3x minus 5. Now, yesterday, I think it was the last thing we talked about from the notes. Yes. The last thing in the section is end behavior models. Okay? What is the difference between a right end and left end behavior model? Not a trick question. I could ask a third grader that question and they should be able to say, oh, Miss Twitty, the difference is left and right. And I would say, well, why does that make a difference? Well, if I told you to go out the door and turn left, or I told you to go out the door and turn right, you'd end up in very different places, wouldn't you? Okay. So if I'm looking at a left-end behavior model, what am I looking for? Something that tells me how the function behaves to the left, but that's much simpler than what I'm looking at. Yes? Okay. So if I'm looking for that, what was the definition of a, and I don't know if I want to go into the specifics of the end behavior model, because that's what the directions said, right? An end behavior model. What is the difference between them asking you for a right, left, or an end behavior model?
We looking for one that like makes both sides.
That's right. We're looking for one that tells us about both sides. So if you think about it individually, you'll do better probably. Okay. So what I want to know is what makes it. What is the definition of a right end behavior model? Where am I when I go to the right on the coordinate plane? Towards positive infinity, right? So the limit as x approaches infinity of f of x over g of x equals 1. And remember I said it doesn't matter which one you put where, because I just want the limit to be 1, yes? So as long as I end up in the same place as this function takes me, then I've done my job, right? Okay? So let's look for something simpler than what's on the top to talk about, okay? What was the trick that I taught you in pre-cal about end behavior? Where do you need to look? And I asked you this yesterday. At the leading term, right? What is the leading term? Not the first term. It's the term with the highest degree. On the top, what is that? Okay, so what I would like to see you do as far as you're thinking on paper is come out here and put an arrow, not an equals because it's not equal, but for our purposes, it is what we need, right? Okay? And we're going to do the thinking and then we'll come back and prove that our answer is right, okay? So that means that on the top, what do I care about? Just x. Yes? How about the bottom? 2x squared. So far so good. Now I can put equals because I'm going to take my truncated version of this function and I'm going to reduce it. Okay? So this is equal to what I just wrote. What can I do to that? Why can I take out an x? Because it's multiplying in the denominator. Do not take out an x unless it's all multiplied. You will be wrong. So this is 1 over x with a 2 in front of the x, yes? So what is this animal? You should know it. I'll write it another. Yes, it is the reciprocal function with what done to it? Times a half, because the 2's on the bottom, right? So it's that would be a vertical shrink. But at a glance, you wouldn't see the difference, would you? Okay? So if we're right, what's happening at the right end? Going to 0. How about to the left? Going to 0, yes? Okay. I have to look to see whether, because I have to think about how they want y'all thinking about this. Notice that these are not no calculator problems. So when you're having trouble thinking, that's one of the steps in your process. I admire and expect that you would try to do it without a calculator, but if they allow a calculator, it might be worth looking at it. So let's think about this function from a pre-cal behavior before we actually graph it. Okay? How would you describe the Twitty's quick trick for horizontal asymptotes? Bottom heavy. So what does that tell us? We expect that we have a horizontal asymptote at y equals 0. Because the more of my pre-cal thinking I can lock into before I actually do the calculus part of things, the easier the calculus will be. Is everybody with me on how we knew that? Okay. Well, what did I tell you yesterday about limits and whatnot? With respect to horizontal asymptotes. The limits at infinity are your horizontal asymptotes, right? And so since this is an end behavior model, isn't that what's happening at the infinities, right? Okay. So since this is bottom heavy, it's going to do the same thing that the reciprocal function does, right? So to demonstrate it, to prove that we're right, we could do the limit as x approaches plus or minus infinity. No, let's not do plus or minus. Leave a space to write it though. Plus or minus, we're thinking plus or minus infinity, but we're going to do it as we go and find out if there's a difference. You with me? And then I'll come back and write it that way if it works out. So I've got x minus 2 over 2x squared plus 3x minus 5. So this is a limit of a what? How do you take the limit of quotient? Take the limit of the top, take the limit of the bottom, and do the quotient, right? Okay. So what is the limit as x approaches infinity of the top? Okay, rewind. What is x minus 2? A line with what kind of slope? Positive. And a y-intercept of negative 2, yes? Do you have that line in your head? As I move to the right, what happens to the line? And I mean, like I move way out to the right, what happens to the line? It goes way up there, right? So that would imply that we're heading towards infinity on the top, wouldn't it? Yes? Okay. Big deep breath. Because we're ratcheting it up now. We're not doing it with lines anymore. What's the bottom? A parabola. What do I know about this parabola? It goes up to the right. How do I know that? Because the leading coefficient is positive means it points up, yes? So we have another infinity, but the difference being here that technically there would be an infinity squared, right? So whatever number we're at, and this is where you, and this takes practice, and it may literally be all the way up till the end of April when we're still having this conversation, but technically this is not proof of my point, but it helps me think about it to see it that way. Infinity over infinity squared, because that's not a number. I can't technically square a thing that's not a number. You with me? All right, but here's where you're going. Because if you go back to the ones you did in 2-1 where you had to plug in those horrible little decimals like 0.0001, 0.000001, etc., what that was showing you was that if you had the rest of your life to do limits problems, you could do them all that way. You could just keep plugging in numbers to see what the pattern in your result was. Does that make sense? So when I'm thinking infinity, I'm thinking, okay, I'm dealing with some huge number. I'm going to pick what, if I was in the 5th grade, I would say is a huge number, 1 million, okay? So if I had 1 million on the top and plugged it into the top, it would be 1 million minus 2, right? We would definitely round that to 1 million, wouldn't we? Then on the bottom, what would I have? I'd have 2 times 1 million squared plus 3 times 1 million minus 5. What do I know for a fact? That's going to be significantly bigger, right? If I think about how a parabola is shaped, it goes up super fast. That means that I don't have to get much bigger of a number to get a much bigger result. You follow me? So that's where that infinity over infinity squared gets you thinking in the right direction, which implies 0. Yes? So I got 0 from that.
How come it implies 0?
Where'd you go for the last 30 seconds? Because the bottom blows up and the top blows up, but not quite as fast, or not nearly as fast. If you think about the parent graph, y equals x squared, do y'all see what I'm saying? If I take 1 step to the right, how far up do I go? 1. Right, 2 steps to the right, I go up 4. 3 steps, 9. 4 steps, 16. 10 steps, 100. And that's not many steps away from the center, and suddenly I'm in 3 digits, right? So it wouldn't take me long for it to get, the ratio of how far I went to the right and how far I go up gets much more extreme. Do you see what I'm saying? So at infinity, it's going to be way bigger. Do you see what I'm saying?
So you're saying that
Like we did in
since the top
21.
is so much smaller that it would just be such a small difference?
Yeah, pretty much, yeah.
0.
Exactly.
Okay.
Yeah. Because if the bottom blows up bigger than the top blows up, if you go out far enough, it's going to be 0. Okay? Now, so we ended up at 0. So now let's look at the limit as x approaches infinity of the f of x, or well, the g of x we came up with. And that's what we'll call our little function up here. So let's come back up here to the top and put that as g of x so that anybody that's trying to follow what we're doing will know where g of x came from. So now we're going to do the limit as x approaches infinity of g of x, which is, what's in the numerator? Because now this is a limit of a quotient, right? If I break it down, 1 over 2x. Yes? So what's the top? 1. What is the limit? And now we're going to make this an implies, because we're about to write an infinity, aren't we? Because 2 times infinity is a bigger infinity, right? And since I don't have another infinity to compare it to, I'm not going to compare two infinities to 1 infinity or anything. I'm just going to leave an infinity. You with me?
Wait, why did you? I thought it was just 2. Why was putting infinity?
You thought it was just a 2? It's 1 over 2x. Now x is infinity. What's infinity doubled? It's infinity. Yes? Are y'all with me? So that implies 0. Now, this is why this problem is in this section at this point in your education, because this is forcing you to reckon with everything we just said, right? Infinity, although in your mind it's a clear concept, it's a huge number, right? But it stands for all huge numbers. That's why you can't operate on it like it's x. Does that make sense? So to prove the point here is that if I were to plug in the same huge number into the top of there, I would get 0, right? in the original function when I take the limit, right? So I'm going to pick some arbitrary huge number. Let's say 10 million. All right. So I would end up with 0. In fact, grab your calculators. This might be worth actually seeing to help it make it a little more concrete rather than abstract. And divide 10 million by 10 million squared. Divide 10 million by 10 million squared. And what did we get? 1/10 millionth? Okay. That actually makes my case. It's as crazy as that sounds. So I'm going to write this in a different color so you realize, so you'll remember what we were doing, and you might need to make yourself a note. So I'm going to write 1/10 millionth. So I'm going to put 1 over 10 million. Now, can we agree, for the sake of our conversation, that that is not 0? It's approaching 0, but it's not 0. Agreed? All right. Well, then when I go to 1 divided by, because the number that we're talking about letting infinity be is what? 10 million, right? Okay. So what is 1 over infinity? 1 over 10 million. So when I ask myself have I met the limit as x approaches infinity of f of x over g of x, the answer is yes, because now I can do 1 over 10 million divided by 1 over 10 million, and what would I get? 1? Yes? I would get 1. So that's why we meet the requirements of the definition. Now, let's go back to our negatives. What would happen if I plug a negative giant number into f of x? It's going to be the same thing, right? It's going to be a tiny negative, but it's still going to be approaching 0, right? So all the arguments we just made still apply, even when they're negative, right? How about the g of x? Same thing, right? So that means now I can go back and stick a plus or minus in both places, right? So my end behavior model, let's call it h of x. Well, actually, no, we already called it g of x. Oops, sorry, I hit the wrong button. So g of x equals 1 over 2x. And we have proved that it is the correct one. And it's okay if some of you are hyperventilating right now. It either means one or two things. You signed up for the wrong class, or you are where most calculus students are in chapter 2, which is like, I can do the problems, but I have no idea what she's talking about. Okay? So if you're in option 2, you're okay. If you're thinking, oh dear God, I've signed up for the wrong class, come talk to me. All right, number 4951. And the irony is that it's always the wrong people who come and talk to me. I'm like, shut up and get out of here. And the ones that need to come talk to me never do, and then they wonder why they struggle later. All right, 4951. Really, Marquise?
Like this?
Okay, no more Bojangles for breakfast. Is that what you had yesterday?
No.
What was the fast food breakfast you had yesterday?
I didn't eat yesterday.
Was that day before? Oh, okay. I was trying to find some reason that your brain might have been sluggish yesterday while we were talking about this. Or maybe it was actually Tuesday. Do y'all not remember this? I'm going to read the directions aloud, and I want somebody to explain to Marquise why I'm saying these things to him. Beyond the fact that I just get great joy from messing with him. Leave that aside. The directions here say, use the graph of y equals f of 1 over x to find the limit as x approaches infinity of f of x, and the limit as x approaches negative infinity of f of x. We're all staring at our hands or across the room saying, please, Miss Twitty, don't call me on this one. No one? Not a one. And I told you this is a very powerful trick to remember, and now you're supposed to remember it. So I'm going to go back and find the problem that I showed it to you on, if I can remember.
What is that just?
We just did this. Did I not walk over to the board? And it was cosine, I want to say it was cosine x over something. And I graphed it. That was the one we zoomed in on and it went crazy? Ooh, yeah, now we're having the epiphany, right? I swear it was a homework problem. maybe it was in our notes when we were talking about the sandwich theorem. But I was thinking it was a ratio of cosine, maybe cosine x over x or something. Graph that right quick, see if I'm right. We'll just use that one as our example. In fact, better yet, let's use our good buddy y equals sine x over x. And just so you'll know, do not come to class without your calculator. When I say graph something, graph it. Don't think I don't need this because I'm telling you to graph it for a reason. So graph sine x over x, which we should know fairly well. What does that one look like? Remember, we talked about the fact that it peaks on the y-axis when you expect sine to go through 0 at the y-axis? Yes? Because it's technically a combination of the sine function and the reciprocal function. So at the y-axis, they do dramatically different things. One goes to infinity, one goes to 0. Yes? That's why we wound up in the middle somewhere around 1. Yes? With the whole? Okay. So what would the limit as x approaches infinity of that graph be? 0 in either direction, right? So we could actually make that a plus or minus statement, couldn't we? How about the limit as x approaches 0? 1. Now go back and leave that graph on your screen and graph the same function, but instead of the x's, put in 1 over x's. So you're going to have the sine of 1 over x divided by 1 over x. Graph that. And then I'm not going to say anything else after you get that picture. I want someone to explain to me why I just had you do that.
Oh, it's backwards.
It's backwards. So the limit at infinity for sine x over x is equal to the limit for sine of 1 over x over 1 over x.
You said none of them.
Let's rewind. What is the limit as x approaches infinity or negative infinity of sine x over x? 0. What is the limit as x approaches 0 of sine of 1 over x over 1 over x?